Everyone. I am Muskan from BSc Chemistry Honors 3rd year. Today I am going to discuss the chapter Raman Spectroscopy of the Pradeep's Physical Chemistry Volume 3. Raman Spectra. It is a special type of spectroscopy which deals not with the absorption of electron but deals with the scattering of light by the molecules. It is observed that when a substance, which may be gaseous, liquid or even solid, is irradiated with monochromatic light of a definite frequency mu, a small fraction of light is scattered. Rayleigh found that if the scattered light is observed at right angles to the direction of incident light, the scattered light is found to have the same frequency as that of incident light. And this type of scattering is called Rayleigh scattering. Professor C.V. Raman of Calcutta University, however, observed in 1928 that when a substance is irradiated with monochromatic light of a definite frequency mu, the light scattered at the right angles to the incident light contained lines not only of the incident frequency but also of the lower frequency and sometimes of the higher frequency as well. The lines with lower frequency are The lines with lower frequency are called Stokes lines, whereas the lines with higher frequency are called anti-Stokes lines. Raman further observed that the difference between the frequency of the incident light and that of a particular scattered line was constant depending only upon the nature of the substance being irradiated and was completely independent of the frequency of the incident light. If Vi is the frequency of the incident light and Vs that of a particular scattered line, the difference is called Raman frequency or Raman shift. Thus, the Raman frequencies observed for a particular substance are characteristic of that substance. The various observations thus made by Raman constitute what is called Raman effect, and the spectrum observed is called Raman spectrum. Thus, in a simple way, the Raman spectrum may be represented as showing in this figure. Now, explanation for observing Rayleigh lines and Raman lines. When the incident photon hits the molecule, the collision may be elastic or inelastic. Elastic collision means that the colliding particles will return with the same energy. Thus, the scattered photon has the same frequency as that of the incident photon. This explains Rayleigh scattering or the Rayleigh line. However, if the collision is inelastic, still the law of conservation of energy will hold good. Total energy before collision and after collision must remain the same. Thus, some energy may be transferred from the incident photon to the molecule so that the scattered photon has the lower energy and hence lower frequency. This explains the occurrence of Stokes lines. Alternatively, some energy may be transferred from the incident photon to the molecule so that the scattered photon has higher energy and hence higher frequency than that of incident light. This explains the occurrence of anti-Stokes lines, and this explanation may be further elaborated as follows. When the photon strikes the molecule, the energy is absorbed by the molecule and it gets excited to some higher energy level. Now, if it returns to the original level, it will emit the same energy as absorbed, and thus we have Rayleigh scattering. However, in most of the cases, the excited molecule does not return to the original level. It may return to a level higher than the original level, thereby emitting less energy than absorbed. This explains the occurrence of Stokes lines. Thus, a part of the energy of incident photons remains absorbed by the molecule so that the molecule has higher energy than before. Alternatively, the excited molecule may return to a level lower than the original level. Thus, more energy is emitted than absorbed. This explains the occurrence of anti-Stokes lines, and in this case, the molecule has less energy than before. Levels have been shown equally spaced for the sake of convenience. Now, the polarizability of the molecules and Raman spectra. The Raman effect arises on the account of polarization of the scattering molecules that is caused by the electric vector of electromagnetic radiation. The induced dipole moment depends upon the strength of electric field and the nature of molecules, and we can write mu is equal to alpha E, where the quantity alpha depends upon the nature of the molecules, and that is called the polarizability of the molecule. Thus, polarizability is the ratio of the induced dipole moment to the strength of the electric field. In the case of atoms or spherically symmetrical molecules like SCH4, SF6, etc., same polarizability is induced whatever be the direction of applied electric field. They are said to be isotropically polarizable, and such molecules are said to be isotropic molecules. In the case of all diatomic molecules, homonuclear or heteronuclear or non-spherical molecules, the polarizability depends upon the direction of electric field. For example, in the case of H2 molecule, the distortion produced is more when the electric field is applied parallel to the bond than when it is applied perpendicular to it. And such molecules are said to be anisotropically polarizing. Types of molecules showing rotational Raman spectra. A molecule scatters the light because it is polarizable. Hence, the gross selection rule for a molecule to give a rotational Raman spectrum is that the polarizability must be anisotropic, such that the polarizability of the molecule must depend upon the orientation of the molecule with respect to the direction of electric field. Hence, all the diatomic molecules, linear molecules, and non-spherical molecules gives the Raman spectrum, such that they are rotationally Raman inactive. On the other hand, spherically symmetrical molecules such as CH4, SF6 do not give the rotational Raman spectrum, that's they are rotationally Raman inactive. In fact, this is one of the reasons for the importance of rotational Raman spectroscopy over infrared spectroscopy, because the latter requires that the molecule must have a permanent dipole moment, whereas the former only requires that polarizability of the molecule must change during vibration. Explanation of Raman effect in the terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating is not constant but varies with the frequency of vibration and rotation. It is the sum of the two parts. Now, equilibrium polarizability. The polarizability when the atoms of the molecule are in their equilibrium position, and the sum of the polarizability of the molecule due to the various rotational and vibrational motions, each term depending upon the frequency of rotation and vibration. Thus, alpha is equal to alpha naught plus summation of delta alpha n by delta r rn cos 2 pi v n t, where alpha n is the polarizability associated with the nth rotational and vibrational mode, and Rn is the maximum displacement. Further, electric vector of the radiation varies with the time. Substituting the values of alpha and E, we get this. Expression consists of three terms. The first term has the frequency of incident radiation and represents the Rayleigh scattering. The second term contains V naught minus Vn and represents Stokes lines, whereas the third term represents the anti-Stokes lines. Now, the quantum theory of the pure rotational Raman spectra of diatomic molecules. The selection rule for the pure rotational Raman spectra of diatomic molecules are delta Z is equal to 0 plus minus 2. The selection rule delta Z is equal to 0 corresponds to the Rayleigh scattering, whereas the selection rule delta Z equals to plus minus 2 gives rise to Raman lines. We know that energy of rotational level is given by mu equals to Vz into Z plus 1. When a transition takes place from lower rotational level with quantum number Z to higher rotational level, then the energy absorbed in the terms of wave number will be this. For the selection rule, delta Z equals 2 plus 2, delta mu bar is equal to B into 4Z plus 6, where Z equals to 0, 1, 2, 3. Again, for the selection rule, delta Z equals to minus 2, delta mu naught equals to minus B, 4Z dash plus 6, where Z dash equals to 0, 1, 2 and 3. Now move to the another ones. Combining the results of the equation, the wave numbers of the lines obtained in the Raman spectrum is, here mu I represents the wave number of Rayleigh line, plus sign gives the lines with higher wave number called anti-Stokes lines, and minus sign gives the lines with lower wave numbers called the Stokes lines. Intensities of the lines of the pure rotational Raman spectrum. As explained earlier, the intensities of lines depend upon the population of initial level from where the molecules are excited or de-excited to the final level. Since the population of rotational energy levels is as shown in this figure, therefore the intensities vary in a similar manner. Application of pure rotational Raman spectra. From the pure rotational Raman spectra, noting the separation, the value of B can be obtained, from which the moment of inertia and the bond length can be calculated. Quantum theory of the rotational vibrational Raman spectra. For the large molecules, the lines obtained due to rotational transition are so weak that they are beyond resolution. Hence, we have pure vibrational Raman spectra, for which the selection rules are same as for the pure vibrational spectra discussed earlier. However, in the case of diatomic gaseous molecules, the resolution of rotational fine structure is sufficient and can be studied. Thus, diatomic gaseous molecules gives the rotational vibrational Raman spectra, which can be explained as follows. Now move to the another piece. This is the rotational vibrational spectrum of a diatomic molecule. Selection rule for the transitions are delta mu equals to plus minus 1, delta z equals to 0 plus minus 2. However, at the room temperature, as most of the molecules are in the lowest vibrational level, therefore the significant vibrational transition is from mu equals to 0 to the 1, called fundamental vibrational transition. Restricting ourselves to the vibrational transition only, the results obtained are as follows. For delta z equals to 0 called Q branch, delta z equals to plus 2 called S branch, delta z equals to minus 2, delta mu bar is equal to WE 1 minus 2xe minus B into 4zs plus 6. Representing the values for Q, S and O branches and the wave number of the Stokes lines will be as follows. We have considered the case for delta mu equals to plus 1, which represents Stokes lines, and the anti-Stokes lines are those for which delta mu equals to minus 1. They are usually weak because very few molecules are in the excited vibrational state initially, and the rotational transition accompanying the vibrational transition and the rotational vibrational Raman spectrum is advantages of Raman spectroscopy over infrared spectroscopy. Raman spectroscopy has a number of advantages over infrared spectroscopy as briefly explained below. Since Raman frequencies are independent of the frequency of the incident radiation, hence by suitably adjusting the frequency of incident radiation, Raman spectra can be obtained in the visible spectrum range, where they can be easily observed rather than the more difficult infrared range. Raman spectra can be obtained even for the molecules such as O2, N2, Cl2, which have no permanent dipole moment. Such a study has not been possible by IR spectroscopy. Raman spectra can be obtained not only for gases but even for liquids and solids, whereas the infrared spectra for the liquids and solids are quite diffuse. Because of the ease with which the Raman spectra can be studied, the molecular structure of a large number of compounds have been determined by Raman spectroscopy. However, infrared spectroscopy method continues to remain popular. Experimental arrangement for the Raman spectra is shown in this figure. The fraction of the light scattered is so low that normally very weak Raman lines are observed. Hence, to detect these lines, it is necessary to use a powerful source of incident light. Earlier, mercury vapor lamps were used, which gave an intense monochromatic radiation of the wavelength 4358 angstrom. However, with the development of lasers, which are very powerful sources of monochromatic radiation, Raman spectroscopy has been greatly revolutionized. So, thank you so much. That's all about the Raman spectroscopy.